Welcome everybody to the final exam review. So, just like we've done in the last exam review, I'm going to give you a bunch of different questions. All of these questions are going to come from a previous final exam that I've given. Now, this is not the lab final. This is the class final that we're going to go through. I will do some calculations as if it was like the lab final, but the lab final is just going to ask you, hey, if I have this hypothesis, what test do I run? You run it in RStudio and tell me whether my hypothesis is supported. That's what the lab final is about. This final and the questions you see here are more what I'm going to ask you for the final. It's going to be less about calculate this, tell me whether it's supported, and more about some other concepts that are out there. So let's go ahead and begin with the data. So here are the data, and these are actually data that you've seen in the past. This is the participant number, the club, whether they own a car, happiness in January, happiness in March, your residence, your GPA, and the number of parking tickets. Those are the variables, and you can download them here. That'll be exactly the same way that we're going to do it for the final. So let's begin. Okay, so this question is asking, what is the mean for happiness in March? Easy enough. Let's go ahead and look at it in two different ways. So first, let's go ahead and look at the data on Excel, and then we'll look at it in RStudio. We can do it either way. Now remember, the question is asking, what is happiness, X bar is the mean for happiness in March. So let's go ahead and try and do this for happiness in March. This will be equals the average of all of these. 5.6875. Now, we'll always go to two decimal places in our final answers, so we're going to go to 5.69. Now, the other way we can do this is in RStudio. So here's my RStudio. I have the data, but I haven't attached it yet, so let's go ahead and attach it. Final exam data. And then I'm just going to ask for the mean of happiness in March. And there it is, 5.68775. So when we do this, we should put in 5.69. 5.69. Okay. Next question, what is the mean for parking tickets? X bar is the mean, that's all that's asking. So let's do this in, let's just go ahead and do this in RStudio, might as well. Mean, in parentheses, parking tickets, 1.625, we should say 1.63 in our answer, or we can do it the other way, which is on Excel. Just add them up and divide. So we'll just do average of all of these. And we get 1.625. It's the same thing. 1.63 is the answer. It's just the average. What is the sum of squares for happiness in March? So this is asking for us to calculate the sum of squares. And this is a little bit harder to do. There's a couple of easy ways to do this, and let me show you how to do this in Excel, because you can do the calculations in RStudio, or you can just do the addition and subtraction. So remember, we're doing the sum of squares for happiness in March. All right, so sum of squares for happiness in March. Let me show you the easy way and the hard way. I'm going to insert some something here just because we're going to have to square some stuff. So I'm going to insert some more. There we go. Make some room. So the mean, if you remember, was 5.68 or 69, right? And then the sum of squares needs to be the sum of the deviations squared. So the deviation square function will give that, all right, which is DEVSQ in Excel. So if you just do this, it will do that. right? And you get 1.09 minus 1.09.4375, or you can just do it the old-fashioned way, get the deviations, which is x minus x bar, and x bar is the mean. And so I'm going to put a little dollar sign right there that says, make sure that you don't move, because I'm going to pull this down in a second. Dollar, dollar. This says I want just E18. I don't want you to ever move from that. And when I do this and pull down, come on. That's what I get. And when I add those all up, I'm going to get 0 because those add up to 0, right? So you've got to square them. So this is this squared. Do that. And now the sum of this is going to be 109. Come on. 109.4375 is the same thing. 109.44 is what we're going to put in. Okay, what is the sum of squares for parking tickets? Same thing as the last question. Let's go ahead and do it. Sum of squares for parking tickets. Let's move this over so we can see it a little bit better. Get those a little bit later on. So the easy way to do this is just to say, give me, so this is the mean up above here, right? So this is the mean, and this is this sum of squares. So equals deviation squared of all of these, the data that we want about. There they are. Oh, I messed up something. Here we go. Let's try that again. Oh, it thinks I only wanted one. I don't know why I double clicked there again. There we go. 97.75. We can do it the old-fashioned way. Equal, this is deviations. So equals this minus the mean, which, whoops, come back me. You'll see what those things on the side are in just a minute. And I'm going to put my little dollar signs on there to keep it in place. And then deviation squared is each one of these squared. Then I'm going to add them up. The sum of all of these, 97.75, the same thing. 97.75 is the answer. Okay, what is the variance for happiness in January? You can do this several different ways. You can just calculate it, right, from the deviations. Okay, but now we're looking for happiness in January, this part right here. So the easiest way, let me just get rid of this mean and sum of squares for the other one. So happiness in January, one easy way in Excel is equals variance of the sample, right? This is a sample, so equals variance of a sample, and then just add them all up. That works fine. So this is the variance, 3.06. All right. The other way to do this is to get the standard, the sum of squares. And you can do it the old way that we did before, where you deviations squared, or you can just use deviations squared. So you'll get this. And then you take it, this will be the sum of squares, and then the variance is this divided by n minus 1. So equals this divided by n minus 1. N is 16, so n minus 1 is 15. And we get 3.0625. It's the same thing. 3.06 is what we're going to put in. What's the variance for GPA? Let's do that the same way we did it for happiness. So I'm going to move this over. Okay, I'm going to erase these, and variance is going to be var.s. That's one way to do it. I messed it up. var.s. I need the parentheses in there. Try this again. I keep messing up on the way I'm clicking. There it is. This is the variance. All right. Or you can get the sum of squares divided by the n divided by n minus 1 equals deviation squared equals this divided by n minus 1. N is 16, so n minus 1 is 15. Look, it's the same, 0.598, and we're going to round up to 2 decimal places, so in this case it's going to be 0.60. 0.60 is going to be the right answer for us. 0.60. Okay. Next question. If I have one parking ticket, what is my z-score? All right, so a z-score is x minus x bar over the standard deviation. All right, so there's several different ways we could do this. We need to take x, which is 1, because I have one parking ticket, minus x bar, whatever the mean is for parking tickets, divided by the standard deviation. So then we can do that. There's a few ways we're going to do this, so let's do it on Excel first, then we can do it in RStudio if you want to. So for parking tickets, I know that my mean is 1.625, okay? I know that my sum of squares is going to be 97.75. That means my variance is going to be this sum of squares divided by n minus 1. N minus 1 is 15. Okay, and the square root of the variance is the standard deviation. So equals square root of that. That should be our standard deviation. So our z should be 1, remember, because our x is 1. Let me go ahead and put parentheses in here. It's 1 minus the mean, which is 1.625, divided by the standard deviation. Negative 0.244. All right. Now here's another way we can do this. We can do this in RStudio if you want. Let's go ahead and do SD for parking tickets. 2.55. Now look, let's see if that's similar to what we had before. 2.55, that's the standard deviation. So we could do the same calculation using RStudio if we would like to do that. We would do 1 minus 1.625. That's the mean for parking tickets, divided by 2.55, 776. Negative 0.24. Let's see if that's the same as what we got in Excel. Negative 0.24. So negative 0.24 is our answer. Negative 0.24. If I have GPA of 3.5, what's my z-score? Okay, so z-score is x minus x bar divided by standard deviation. Here it is in Excel. Here's GPA. This is the variance. Remember, we calculated the variance. So the standard deviation, which is just S, not S. Come on. Standard deviation is going to be the square root of this right there. Okay. So our x, let's remember what our x is, because I forgot. It is 3.5. Okay, so if somebody has a GPA of 3.5, their z-score is going to be 3.5 minus the mean, which is going to be, do I not have the mean here? I don't have the mean. All right, well, I'll just tell it to do it for me. Okay, divided by the standard deviation. 0.6868. That is the z-score. Let's go ahead and try this with our studio. Let's get the mean of, we can actually just tell it to do what we want to do. So I want it to do 3.5 minus the mean of GPA, okay, divided by standard deviation of GPA. 0.6868. Is that the same thing as what we got before? And the answer is, look at that right there, 0.6868. So we're going to point the z-score of 0.69. That's what we're going to put in there, 0.69. If I have a z-score of 2.5, how many standard deviations is my score above the mean? A z-score is the number of standard deviations above the mean. 2.5. You are 2.5 standard deviations above the mean if you have that z-score. That's it. If I think that happiness in March and happiness in January both predict your GPA, what test will I use to run my hypothesis? All right, so both happiness in March and happiness in January predict your GPA. So happiness in March is continuous, happiness in January is continuous, and we want both of those to predict my GPA, which is also continuous. So I've got two continuous variables predicting one continuous variable. That is a multiple regression. Multiple regression because it's two continuous variables predicting one continuous variable. So it's to both happiness in March and happiness in January together predicting your GPA. If I think that both your GPA and number of parking tickets you have predict your happiness in March, what statistic will I use to test this hypothesis? So think about this. GPA is continuous. Number of parking tickets is also continuous. They're predicting one other continuous variable, happiness in March. That's a multiple regression. I know the population has a mean GPA of 2.0. I also know that the population standard deviation is 1. Okay, so think about this. I know mu and I know sigma. So I know both the mean of the population and I know the standard deviation of the population. I think that this sample's GPA is significantly higher than the population's. What statistic do I use? Now, you do not use a single sample t-test because you know both the mean of the population and the standard deviation of the population. That is a z-test. I think that students who own a car and live on campus have significantly more parking tickets than students who don't have a car but live on campus. And any student who doesn't live on campus, what statistic would I use to test this hypothesis? Okay, students who own a car. So owning a car is yes or no. So that's two levels of a categorical variable. Parking tickets is going to be the outcome, the dependent variable, and that's continuous. All right, so a categorical variable, own a car or not, that's two levels. However, I think that students who don't have a car but live on campus and any students who doesn't live on campus. So that means that there's another factor that I care about that is living on campus. That's another categorical factor, and it has two levels. Okay, so that means that I've got a 2 by 2. This is a factorial analysis of variance that we would do. I think that students who are in a yoga club have a higher GPA than students in the other clubs. What statistic will I use to test this hypothesis? All right. Students who are in the yoga club have a higher GPA than the students in the other clubs. Well, if you look at that variable of club, you will see that there's the basket weaving club, the chess club, and the yoga club. those are 3 categories in one categorical variable. So 3 levels of the categorical variable. And the outcome is GPA, that's continuous. So I have one factor, one independent variable with 3 levels on a continuous variable. I have to use a one-way analysis of variance. It's one way because there's only one factor and it has more than 2 levels. I'm using a one-way analysis of variance. If I think the students who live on campus have a higher GPA than the students who live off campus, what is the pooled variance? All right, so students who live on campus versus off campus, this would be an independent samples t-test. Okay, this would be an independent samples t-test, and I need to get the pooled variance. So the way I would do this is, first, I need to separate those who live on campus from those who live off campus. There's a couple of ways I can do this. I think the easiest way is to sort the data, but you'll have to create 2 columns. If you're doing this in Excel, you've got to create 2 columns. I'll show you how to do it both in Excel and just doing it with the basic calculation. All right, so here we go. I'm going to sort these data based off of the residence, because residence is on or off campus, right? And that's going to give me all the off campuses right here. These are all off campus GPAs. And then these are all on campus GPAs. And I would put this into 2 columns. So this group right here is right here, 1.5, etc. And then this group right here is right here. Okay? So then what do I do? Well, if I have the data analysis tool pack here, then I go to data analysis and I click on t-test 2 samples assuming equal variances. That's the independent samples assuming equal variances. I click OK, and then I make sure that I have the right ones in the right place. So I want this to be my first group, and on campus is my second group, and then I have them labeled. When I push OK, this is what I get. It automatically calculates my pooled variance. 0.64 is going to be my pooled variance. Now, if you don't want to do it that way, then we can do it another way, and then we can calculate the variances and use the actual formula. So let's go ahead and look at that formula to remember, to remind you what it looks like. So this, where are you, formula? Come on, formula, one way. Here's my t-test. So when I'm looking at pooled variance, where are you, pooled variance? This right here, S squared P, that is the pooled variance. So this would be the formula that I need to do. N sub 1, that's the number of people in the first group minus 1, times the variance of that group. N sub 2 minus 1 times that variance all over the degrees of freedom, which is N sub 1 plus N sub 2 minus 2. So let's go ahead and do that right now, looking at our old data. So here's my 2 groups that I was looking at, off campus and on campus. So let's go ahead and get the variance for both. This you can calculate the old-fashioned way, or you can do var.s, which is the variance of a sample. Okay, that's the variance that I want. And then this one, let me just make sure that it's not messing up by giving us extra. So I don't want 010, I want that to be 08. That group. Okay, good. N for each group is going to be, let's count them, 1, 2, 3, 4, 5, 6, 7, 8, 9 for this group, 9 for this group, and this is going to be 7 for this group. Okay, so the way you do this is you take n minus 1 times the variance plus n minus 1 times the variance. All right, so I need 8. So this is going to be n minus 1 times the variance for off campus. So this is going to be n minus 1, which is 8, times the variance right there. And this is going to be n minus 1, which is 7 minus 1, which is 6, times the variance. All right, we add those together. So this plus this. And then we divide that by the degrees of freedom. Degrees of freedom is n sub 1 plus n sub 2 minus 2. So it's going to be 9 plus 7 minus 2. So it's going to be 16 minus 2 is 14. That means that the pooled variance is going to be this divided by 14.64. Let's see if that's the same as what we calculated before. 0.64. There it is. Okay, for the next questions, we're going to use these data. Now, these data are deviations. They are not raw scores. So I'm going to go ahead and just copy these over into my Excel document and see if they're going to let me keep them in the Excel. If not, then I can calculate them separately. Let's see if we can do this. Because these are new data, I'm just going to go ahead and get a brand new sheet for all of these. And let's see if it's going to let me. Yeah, it's not going to let me do it. So I'll go ahead and enter them in. So I've got participant 1 through 6. All right. Deviations, sleep, deviations, cookies, and deviations, pets. Okay, deviations sleep are -1, 0, 1, -1, 0, and 1. And for cookies, -1.5, -1.5, 1.5, -0.5, 0.5, and 1.5. And then for pets, it's a little bit different. -0.66667.3, 1, 2, 3, 4, 5, 6. Trying to keep everything the same number of decimal places. 1, 2, 3, 4, 5, 6. And then again, -0.1, 2, 3, 4, 6s and a 7. And then 2 more 0.33s. All right, let's check that. Make sure it looks right so that we don't make any mistakes. -1, 0, 1, -1, 0, 1, -1.5, -1.5, 1.5, -0.5, 0.5, and 1.5, -0.66667, 0.33, 0.33, -0.7, 0.33. Okay, great. That's going to look good. So what do we need to do then? Let's figure out what we need to do with these data. Now over here it says, what is a covariance? Covariance between cookies and pets. We need the covariance between cookies and pets. All right, how do we do covariance? So if you remember, right, when we did our covariance, we did the sum of the deviations multiplied by each other. So deviations of one times the deviations of the other, you add them up and you divide it by n minus 1. So let's take a look and see what we've got with our data right here. We want the deviations, put this back, between cookies, covariance between cookies and pets. So let's do cookies and pets. Cookies and pets. So I need to multiply the deviations. I need to multiply cookies times pets. Now, since these are already deviations, I don't have to mess with creating the deviations. I just multiply this together, and I do it for all of them. Okay? Then I'm going to add them up. I add up all of these, and they're in the product. And then I divide it by n minus 1. N is 6. I divide it by n minus 1, which is 5. So the covariance is going to be this divided by 5.40. So the covariance is going to be 0.40. Calculate R for cookies and sleep. Okay, so let's calculate R for cookies and sleep. So here's cookies right here, and here's sleep right here. Okay, so how do we get that? Well, the easiest way, you remember how to, and when we're calculating, is to take our covariance divided by the standard deviations. All right? Or we can do the sum of the z-scores over n minus 1, or we can do this big, long, whatever this is, right here. Okay? Let's do this first one, covariance divided by the standard deviations. But remember, well, you're like, wait a minute, but I only have deviations. How am I going to do this? Well, it's going to be pretty easy because we already know how to calculate this stuff. So let's get the covariance and then divide it by the standard deviation, the product of the standard deviation. So let's find it right now. So just to remind us what we're doing, we're calculating R for cookies and sleep. Cookies and sleep. So let's go ahead and get the sum of squares and variance and standard deviation. Now we can't do it the easy way because these are not raw scores. So that means we're going to have to take these deviations, square them, and add them up. So what I'm going to do is I'm going to add a column between these. Come back. There we go. Which is going to be deviations squared. All right? This is just like we used to do. It is this squared. Take all of them, and then the sum of squares is going to be the sum of all of those. 4. No big surprise there, right? We do the same thing for cookies. Whoops. The deviation squared is going to be this. I should make this larger for you. I'm sorry. I've been messing with this. So this is this squared. We add them all up, and then we get the sum. Right? The variances then equals this divided by n minus 1. So n is 6, n minus 1 is 5. Same thing here. And then the square root of that will be our standard deviation. I need to say equal. Okay? So those are our square roots for sleep, or sorry, standard deviations for sleep and standard deviations for cookies. So what we're going to do next is we are going to get the covariance. So remember, to do the covariance, we need the product of the deviations of sleep and cookies. So that is the deviations, not the deviation squared. So it's this times this. Okay, the deviation sleep time, the deviation cookies. We're going to do that for each of them. All right. Whoops, I did too many. Yeah, those are the original 6 right there. Okay, then we're going to add them up. Then we are going to divide it by n minus 1, right? So if you remember, n is 6, so n minus 1 is 5. Guess what that's going to be? It is this divided by 5, and that's going to be 1. So the covariance is going to be 1. All right, so this is the covariance that we want. Now R is going to be the covariance times, covariance divided by the product of the standard deviations. All right, so here's the product of the standard deviations. It is standard deviation of sleep times standard deviation of cookies. There it is. And that means that R is going to be this covariance divided by the product of the standard deviations, 0.81. Calculate T from R for sleep and pets. All right, for sleep and pets, we need to then calculate everything that we did before for sleep and pets. So we need to get the standard deviations for sleep, the standard deviation for pets, and then we need to get the covariance of sleep and pets, get the R, and then we got to go through the T. So this is going to take a few extra steps to get this one. So let's go ahead and do this. So first we're going to start, just to remind you of what we're doing. We're going to take the covariance of x and y. So we're going to get the covariance, which is the sum of the deviations multiplied by each other divided by n minus 1. So let's do that. That's the covariance. We got to get r, then we got to get t out of it. All right, so here we go. So let's first, we're going to do sleep and pets now, right? Let me make sure I do the right one. Sleep and pets. T for R for sleep and pets. Okay, so for pets, let's go ahead and just do, we need to get the standard deviation like we did before. So I'm going to insert one right here. This is going to be deviations squared. This squared. All right, I'm going to get all of those. Okay, let me get rid of this. All right, then I'm going to get the sum of squares. I'm just going to add those up. Then I'm going to get the variance, which is going to be sum of squares divided by n minus 1. N minus 1 is 5. The standard deviation is going to be the square root of the variance right there. So there's a standard deviation for pets. We already had the standard deviation for sleep. That was over there. But we do not yet have the covariance for sleep and pets. So to do that, we need to get the products of the deviations of sleep and pets. So that is going to be sleep, deviation for sleep, times the deviations for pets, right there. And we're going to get that for all 6 of them. Then we're going to get the sum. So that's the sum of that, 2.006, right? Right there. Then we're going to divide that by n minus 1. Okay. We're going to divide it by n minus 1, which is, let me just make sure we got all this right. The sum of all the j's is 2, good. N minus 1 is 4.0. It's going to be, I didn't realize that they had the same covariance as cookies, and that's interesting. Anyway, doesn't matter. So that's what that is. This is going to be, this is the covariance right there. All right, that's the covariance, 0.40. We take the covariance times the product Okay, the product of our standard deviations equals sleep standard deviation times PET's standard deviation. And then R is going to be covariance divided by the product of the standard deviations, 0.8666. Now, so this is R. We've got R, but we need to calculate T from R. So that means that we've got to use, let's show you we need to use this. R times the square root of n minus 2 divided by the square root of 1 minus r squared. Okay? So let's go ahead and do this. We have r already. N minus 2, n is 6, so n minus 2 is 4. The square root of 4 is 2. All right? So this, well, I'll do it over here on this side. So the numerator is going to be r times the square root of n minus 2. N minus 2 is 4. The square root of 4 is 2. So it is n times 2. When you take that divided by the square root of 1 minus r squared. So let's go ahead and get equals square root of 1 minus r squared. Okay? 0.5. Then that means that our t is going to be this divided by this. 3.46. 3.46 is our t. 3.46. If I sleep for 7 hours, how many cookies do you predict I will eat? Here are the means that I would need. All right, here we go. So for this is going to be a linear regression. This is a linear regression. X is going to be 7. So if I sleep for 7 hours, how many cookies do you predict I'm going to be? So that means I need the covariance between sleep and cookies. Let's see if I have that already. The covariance, sleep and cookies, the covariance is going to be right here. This is the covariance. The covariance is 1. Okay. All right. Remember what I did is I multiplied them all, and I added those up, and that equals 5. And then I divided by n minus 1, which is 5. So this is the covariance. It's 1. The covariance is 1. All right. So I know that the covariance between those two is 1. When I am looking for a linear regression, I need to calculate B, right? B is the covariance of xy divided by the variance of x. Okay, so what is the variance of x? So we know that our covariance is 1. The variance of x, if you remember the original question says, if I sleep for 7 hours, so that means that sleep is going to be x. Okay, so we need the variance of x, variance of sleep. So if you look right here, you'll see that we already calculated the variance of sleep right here. When we squared them all, added them, divided by n minus 1, 0.8. That's the variance right there. So I need to get B. So B is going to be the covariance of sleep and this is sleep and cookies, right? Divided by the variance of sleep. 1.25. All right? Okay. So then what do I need to do? I also need to get the Y-intercept. So how do I do that? Here it is right here. A equals the mean of Y minus B times the mean of X. All right. Y is going to be cookies. X is going to be sleep. Okay. So let's go ahead and take a look at the information that we have. Y is cookies, 13.5. Sleep is X, that's the mean is 5. So cookies, 13.5, sleep is 5. So here we go. So the mean of X is the mean of sleep. Now remember what that is. I just forgot in all honesty. It's 5. Okay. Mean of Y is 13.5. That's how many the mean of cookies. And for us to get the Y-intercept, we need to get the mean of cookies minus B times the mean of sleep. All right, so A is going to be this minus this times this. 7.25. The question asked, if I sleep for 7 hours, how many cookies am I going to eat? So Y equals BX plus A. So X is going to be 7. That means I'm looking for predicted Y equals Y equals BX. So B times X plus A. 16. 16. So if I sleep for 7 hours, I'd predict that you would eat 16 cookies. The next few questions, we're going to refer to this scenario. Now, what we're going to show you here is we've got several different things talking about GPA, right? So textbooks and flashcards affect your GPA. This is a multiple regression. How do I know? Well, because this is what a multiple regression looks like, right? I've got two variables, textbook use and flashcards, predicting one variable, which is the GPA. So I know that's a multiple regression. What is the number that represents the effect of both textbooks and flashcards on GPA? That is capital R right here. Both of them together, 0.923 is the effect of both of them together. Does reading a textbook alone predict GPA? All right, so what we're looking for here is the beta for textbook, right? So because it asked, does reading the textbook alone predict GPA? Textbook alone, this is the beta. The p-value for that is 0.31. It does not by itself, so that's greater than 0.05. So no, it does not. Does using flashcards alone predict GPA? Well, so now we're going to look at the beta for that one. And here it is. That is less than 0.05. So yes, it does. Okay, we're going to answer each of these independently now. A blank distribution includes all the values of a blank, and the probabilities of the blank hypothesis is blank. Okay, remember how much we talked about this? Sampling distribution predicts all the values of a statistic and their probabilities if the null hypothesis is true. I think the Coloradans are more likely to ski than the normal population. I sampled 10 Coloradans for my study. In the normal population, 50% of the population ski. If I have a two-tailed test, how many Coloradans out of 10 can ski for me to reject the null hypothesis? This is a binomial. So let's go ahead and take a look at a binomial table to see if we have it. Now in this case, we have 10 Coloradans. So let's go ahead and pull up a binomial table. But we need an n of 10. All right. So if the normal population's 50% ski, I'm looking at this group right here. All I'm doing is adding up the two tails. So 0.000977 plus 0.00977. So that means I'd accept 0 or 10. I would reject the null hypothesis. The next one is 1 and 9. If you add up all of those together, you're still less than 0.05. So I would accept that as well. However, once you add up the probabilities of 2 and 7, we're over 0.05 if we add those up. So we are going to only reject the null hypothesis for 0, 1, 9, and 10. 0, 1, 9, and 10. 0, 1, 9, and 10. I think the Coloradans are more likely to ski than the normal population. I sampled 12 Coloradans for my study. In the normal population, 50% of the population ski. I think that 80% of Coloradans ski. If I have a two-tailed test, what is the power for my test? So remember, I'm going to have 12 Coloradans, so that we need to do the same process for Coloradans skiing, and then we need to see which ones we are going to reject the null, and then we're going to look at the same for 80% as well. So let's do that right now. Let's go back to our binomial, and now we're looking at 12. So if you look at this and we add up 0 and 12, we would reject. That's still less than 0.05. And then here, 1 and 11, still less than 0.05. And this is going to get tricky here, because this plus this is 0.032. 0.032. So it looks like we are still going to reject the null with those as well, because if you add up that, let me just do a quick addition on some of these on a new sheet, and we'll see if we can get it to work. So I'll come back binomial. So we need point 0.00244. That's the probability of 0. Okay. The probability of 12 is also 0.00244. It's the same thing. Then we need the probabilities of 1 and 11. Probabilities of 1 and 11 are 0.00293. And this one is also 0.00293. Then we need the probabilities of 2 and 10. And those are 0.016113. Both of those. And if you add those up, you're going to get less than 0.05. Okay? So I'm going to reject the null for 0, 1, 2, 10, 11, and 12. 0, 1, 2, 10, 11, and 12. So now what I need to do is look at, if you remember the question, it says, I think 80% of the Coloradans ski. What's the power? So I just need to go to the 80% part, 0.8, and I need to add these up. Now these, remember, I'm gonna round up to 0.02. So this plus this plus this, 0, 1, and 2, those add up to essentially 0. So really all I'm gonna be doing is adding up 12 plus 11 plus 10 And then I technically do add the other ones, but they're really not going to affect my calculation very much. So for 0, it's essentially the probability is really, really close to 0. For 12, the probability is 0.068719. Probability for 1 is essentially 0. The probability for 11 is 0.206158. Probability for 2 is essentially 0. And the probability for 10 is 0.2833468. When you add all those together, you get 0.558. So that means that the power for this is 0.56. If I think the students who live on campus have a higher GPA than students who live off campus, oh, we already did this. This is the pooled variance one. It was just in the wrong spot. So we already did this one before. That's a repeat question. We can look at that later. I think that my class, by the way, so the answer, if we look back up here, where is it? Come back, pooled variance, just to make sure that we have it in here. There it is, 0.64. Okay, sorry, that was just in the wrong spot. I think that my class eats more candy than the population. I have 100 people in my class. I found that the average number of candy canes eaten in my class is 6. The standard deviation for my class is 5. The average for my population is 4. Assuming alpha equals 0.05, calculate power for this test. All right, so for this one, we need to do a single sample t-test. That is going to be x minus x bar divided by the standard deviation, but not the standard deviation sub x bar. So it's going to be the standard deviation divided by the square root of n. Okay, so let's go ahead and do that first. So x is going to be, for my class, x is 6. All right, so x is 6. X bar, well, it's just actually mu, isn't it? Because it's the populations. Okay. Average for the population is 4. Okay. Standard deviation, which is the standard deviation for my sample, is 5. All right, and n is 100. So I need to get my t statistic, which is going to be, it's going to be x minus mu divided by, not just the standard deviation, it's going to be the standard deviation divided by square root of 100, which is 10, by the way. So my t is going to be 4. T is 4. All right, but what is this thing about the power for the test? How do we do that? Well, here's what we do. Let's go ahead and look at the calculation to remind you how it is. So what we just barely created was our single sample t-test. So what we want to do now is get the d, right? That's the estimated effect size. That is going to be x bar minus mu over just the standard deviation. All right, so let's do that first. X minus mu, so the mean x bar, that's actually my x bar, isn't it? I should say x bar, just to make sure that we're clear that this is actually x bar, not just x. So my estimated effect size is going to be x bar, I need to get the parentheses, x bar minus mu divided by standard deviation, right there. Then that's just the effect size. for me to get delta, delta is going to be my effect size times the square root of n. So if you look at it right here, delta is the effect size times the square root of n. Okay, so let's go ahead and try to do that. Delta is this times the square root of n. Guess what? N is 100, so the square root of n is 10. It's going to be 4. Delta is 4. To find the power, then I look it up on my delta table right here. 4 is the delta, and this is the column for 0.05, which is what I want. So that means my power is 0.98. 0.98. Which of the following are significant in this output? And the answer is none of those are. That's the probability, the p-value right there. None of those is less than 0.05. None of those is significant. How many main effects are represented here? The main effect is the number of factors that you have. All right. Phone and car, and phone by car. Phone is a main effect, car is a main effect, phone by car is an interaction. I have 2 main effects here. What is the mean square for the main effect of phone? Okay, mean square is just the sum of squares divided by the degrees of freedom. So it's 9.5 divided by 1. So the mean square is going to be 9.5, right? In case, I think we have this up if you want to see it. Mean square is the sum of squares of the group divided by the degrees of freedom of the group, right? So sum of squares of the group divided by degrees of freedom, 9.5. What is the F value for the interaction? So that is going to be the mean square divided by the residual. So we take the 5.03 divided by degrees of freedom. That's going to be 5.03. And then divide 5.03 by 7.561. So let's calculate what that is. Equals 5.03 divided by 7.56. 0.665. So 0.67. What is the critical value of a z-test if you have 2-tailed test with alpha equals 0.05? I already know what this is. It's 1.96. But if you ever want to look at it, here's how it looks. This is the old normal distribution, right? And so what you need is a smaller portion, but it's 2-tailed, so it's got to, the smaller portion has to have a p-value of 0.025. So you're just looking for 0.025 in the smaller portion. Here it is, 0.025 in the smaller portion. The z-score is 1.96. That's the critical value. It's always. There's no degrees of freedom for that, so it doesn't matter. Okay. What is the critical value of a z-test if you have a 1-tailed test with alpha equals 0.05? All right, so now we do the same tail, only with a 1-tailed test. Same thing. And that is going to be, we're looking for 0.05 in the 1-tailed. And here it is, right here. It's between these two. Generally do the more conservative 1.64. It'll accept either one because it's going to let it round. 1.64 is going to be fine. What is the critical value of a t for an independent samples t-test where n equals 12? Assume a 2-tailed test alpha equals 0.05. All right, so you need a t-table for this. For an independent samples, it's n minus 2 is the degrees of freedom. So the degrees of freedom of n minus 2, that means the degrees of freedom is 10. And then let's go ahead and look at the t-table for this. Here's a t-table. 2-tailed test, degrees of freedom of 10. Critical value is 2.228. 2.228. N minus 2 is the degrees of freedom. Two-tailed test. Alpha equals 0.05, 2.228. 2.228. What is critical value for a paired samples t-test when n equals 20? Okay, well, with a paired samples t-test, it's n minus 1. So we need a degrees of freedom of 19, and we would do the same process. Degrees of freedom is 19. Two-tailed test right here. So 19, two-tailed test, 0.05, 2.093. 2.093. I think that's it. Let's